Welcome, everyone. Today we're going to dive into a fascinating topic in technical drawing, isometric and oblique projection. Think of isometric projection as a way to show a three-dimensional object on our two-dimensional paper or screen, but with a special twist. What makes it special? Well, it allows us to see all three dimensions, length, width, and height, in a proportional way that looks realistic to our eyes. Imagine you're looking at a cube from a corner. That's essentially what isometric projection gives us. It's part of a larger family called axonometric projection, where the projection plane intersects our three main axes at equal angles. This technique is particularly valuable in engineering and design because it helps us visualize complex objects clearly. Now, let's understand how we can represent 3D objects in different ways. There are three main types of pictorial views that we commonly use. First, we have the isometric view, where all three axes are spaced equally at 120 degrees apart. Imagine a Mercedes-Benz logo. In this view, everything is proportionally accurate, though not necessarily to exact scale. Then we have the oblique view, which is interesting because it shows one face exactly as it is, while the other faces appear slightly distorted. Think of looking at a building from an angle. There are two variations here. Cavalier projection shows full depth, while cabinet projection shows half depth for a more natural look. Finally, we have the perspective view, which is closest to how our eyes actually see things. Objects appear smaller as they get farther away, just like when you look down a long hallway. Each of these methods has its own unique advantages and specific uses in technical drawing. Let's explore the fundamental principles that make isometric projection work. The most important concept to grasp is the relationship between our three axes. Imagine taking three lines and arranging them so they're all exactly 120 degrees apart. These are our x, y, and z axes. This equal spacing is crucial because it ensures our drawing will look balanced and proportional. When we measure along these axes, we use the same scale for all three directions. Now, you might notice that angles in your drawing look different from the actual object. This is normal. A 90-degree angle in real life won't look like 90 degrees in your isometric drawing, and understanding this distortion is key to creating accurate representations. Moving deeper into isometric projection, let's talk about two important concepts: isometric lines and non-isometric lines. Isometric lines are any lines that run parallel to our three main axes. These are the easiest to draw because they follow our basic framework. Think of them as the edges of a cube. They'll always appear as straight lines in your drawing. Non-isometric lines are trickier. These are lines that don't align with our axes, like a diagonal across a face or a slanted edge. These require special attention and techniques to draw correctly. Understanding the difference between these two types of lines is crucial for creating accurate isometric drawings, especially when dealing with complex objects. Here's an important distinction that often confuses students: isometric projection versus isometric drawing. While they might look similar, there's a key difference in how we handle measurements. In isometric projection, we actually scale down our measurements by about 82%, to be precise, 0.816, to account for the mathematical reality of projecting 3D onto 2D. This gives us a technically accurate but slightly smaller representation. On the other hand, isometric drawing uses the actual dimensions without any scaling. It's less mathematically accurate, but often more practical for everyday use. Think of it like the difference between a precisely scaled architectural model and a sketch that captures the essence of the building. Both have their uses, but it's important to know which one you're using and why. Let's explore how to represent different 3D shapes in isometric projection, starting with a cube. the building block of understanding more complex shapes. When drawing a cube isometrically, we begin with those three essential isometric axes we discussed earlier. Imagine you're building the cube step by step. First, mark equal lengths along each axis. These will be your edges. When you connect these points, something magical happens. Your flat drawing suddenly appears three-dimensional. The beauty of isometric projection is that all edges of the cube remain equal in length, just as they are in reality. Moving on to prisms, we apply the same principle, but with a twist. Instead of equal dimensions, we start with any polygon as our base. It could be a rectangle or even a triangle. Think of it like stretching that base shape upward, creating vertical lines to give it height. Picture building a house of cards. You're essentially doing the same thing, but with precise measurements and angles. Now, let's tackle two more fascinating shapes, pyramids and cylinders. When drawing a pyramid, imagine balancing a pencil on its point above the center of a square or polygon base. That point, we call it the apex, is what gives pyramids their distinctive shape. The trick is to connect this apex to each corner of the base, creating those sloping triangular faces. It's like folding a piece of paper into a pyramid. Each fold represents a line in our drawing. Moving on to cylinders. This is where it gets interesting. In reality, a cylinder has circular ends, but in isometric projection, these circles transform into ellipses. It's similar to how a coffee cup's rim appears oval-shaped when you look at it from an angle. We draw these ellipses at the top and bottom, then connect them with straight lines. Remember, while the circular faces become ellipses, the vertical edges of the cylinder remain straight and parallel. This is a key characteristic of isometric projection. Let's break down the process of creating an isometric projection into manageable steps. Think of it as following a recipe. First, just like you'd measure ingredients before cooking, we need to identify our object's dimensions, length, breadth, and height. These are our raw materials. Next comes setting up our workspace, drawing those isometric axes at 120 degrees to each other like a three-pointed star. Now, here's where precision comes in. We carefully plot key points along these axes using our measurements. It's like creating a constellation. Each point has its specific place. Once our points are mapped, we connect them with lines to form edges. Imagine stringing lights between stars. The real artistry comes in adding details. Perhaps there are holes, grooves, or cuts in our object. Finally, if we're showing a cross-section, we can add hatching. Think of it as shading to show what's inside. Remember, each step builds on the previous one, creating a clear, accurate representation of our 3D object. In the real world, isometric projection is like a universal language in technical fields. Engineers use it to design machine parts. Imagine being able to show a complex engine component from all angles in one clear drawing. Architects rely on it to present building layouts. It's like giving someone a bird's eye view while still showing height. In product design, it helps visualize how a new gadget will look before it's even made. Think of it as a preview of the future. And in education, it's an invaluable tool for helping students understand spatial relationships, like having X-ray vision to see all sides of an object at once. However, we do face some challenges. Circular features become elliptical, which can be tricky to draw accurately, like trying to draw a perfect circle while looking at it from an angle. Complex objects with many intricate parts require considerable skill to represent correctly. And sometimes, people get confused between isometric projection and drawing scales. It's like mixing up metric and imperial measurements. Now, let's shift gears and discuss oblique projection. Imagine looking at an object as if you're standing directly in front of one face, but can still see its depth. What makes oblique projection special is that one face of the object appears exactly as it would in real life. No distortion at all. The depth is shown using lines at an angle, like shadows stretching away from the true face. This method is particularly useful in engineering and design because it combines the clarity of a front view with a sense of depth. Think of it as taking a photograph of a building's facade while still showing its side and top. The beauty of oblique projection lies in its simplicity. It's like having the best of both worlds, the accuracy of a 2D drawing with the visualization benefits of 3D representation. Let's delve into the core principles that make oblique projection such a powerful visualization tool. The most fascinating aspect is how it handles the front face of an object. Imagine placing a glass cube directly against a window. The face touching the window appears exactly as it is, with no distortion whatsoever. Now, to show depth, we draw lines at specific angles, typically 30, 45, or 60 degrees from horizontal. Think of these as rays of sunlight casting shadows from that front face. What's particularly interesting is how we handle scaling. While everything on that front face stays true to size, just like looking through that window, we have some creative freedom with the depth. It's similar to how a skilled artist might adjust perspective to make a painting more visually appealing while maintaining the essence of reality. Understanding the distinction between oblique and isometric projection is crucial for choosing the right technique for your needs. Let's compare them side by side. In isometric projection, imagine looking at a cube from a corner. None of its faces appear undistorted, but they're all equally treated with those characteristic 120-degree angles between axes. Now, contrast this with oblique projection, where it's like looking straight at one face of the cube while seeing its sides at an angle. The scaling approach differs too. Isometric keeps everything proportional, while oblique projection lets us play with the depth scaling for better visual appeal. Think of isometric as a democratic view where all faces are treated equally, while oblique projection gives priority to one face. This makes oblique projection particularly useful for objects where one face contains important details that need to be shown accurately, like the front of a building or the face of a machine control panel. Let's examine the building blocks that make oblique projection work. First, we have our receding lines. These are like the trails left behind as we pull our front face into the third dimension. The angles we choose for these lines, whether 30, 45, or 60 degrees, dramatically affect how our drawing looks. Imagine holding a cardboard box and tilting it at different angles. Each angle gives a different sense of depth. Now, here's where it gets interesting. We can choose between full scale and half scale depth. Full scale means we show the actual depth, like measuring the box exactly as it is. Half scale, where we draw the depth at 50% of its true length, often creates a more natural-looking drawing. It's similar to how artists might slightly compress depth in their paintings to make them look more realistic to our eyes. Think of it as a compromise between mathematical accuracy and visual appeal. Let's explore how to handle circles and cylinders in oblique projection. These can be tricky but fascinating shapes to represent. When drawing a circle in oblique projection, we start with a perfect circle on our front face, exactly as we see it. But when that same circle appears on a receding face, it transforms into an ellipse, like looking at a coin from an angle. For cylinders, we're essentially connecting two circles, one staying true and one becoming an elliptical shape. Imagine a can of soup. The opening facing you remains circular, while the other end appears oval-shaped. The vertical edges of our cylinder remain parallel to each other, creating a sense of depth. Drawing these curved shapes might take some practice, but understanding how they transform in oblique projection helps us create more accurate and visually appealing drawings. Moving on to prisms and pyramids in oblique projection, we're dealing with shapes that combine straight edges with various faces. When drawing a prism, imagine starting with its front face, perhaps a rectangle or polygon, drawn exactly as it appears in reality. Then, we extend the edges back at our chosen angle to create depth, like stretching a rubber band. The trick is maintaining parallel lines where needed. Think of it as following the grain in a piece of wood. For pyramids, we begin similarly with the base shape, but here's where it gets interesting. We need to establish the apex point along our receding lines. Picture holding a tent pole at different angles. The way we position this apex point dramatically affects how steep or gradual our pyramid appears. These seemingly simple shapes become powerful building blocks for more complex objects in technical drawing. Let's walk through the process of creating an oblique projection, breaking it down into manageable steps that build upon each other. We begin just as a carpenter would measure twice and cut once, by carefully identifying the true dimensions of our object, its length, width, and height. Next comes what I consider the foundation of our drawing, sketching that front face in its true shape. This is like laying the cornerstone of a building. Everything else will reference back to this face. Then we add our receding lines at our chosen angle, typically 45 degrees, though we can adjust this based on our needs. Think of these lines as paths that guide our eye into the depth of the drawing. As we complete the back face, we're essentially creating a framework, like building the skeleton of our drawing. Finally, we connect all our edges and add the necessary details, bringing our two-dimensional drawing to life with a three-dimensional appearance. Remember, each step is crucial. Rushing through any part is like trying to build a house without a proper foundation. In the world of design and engineering, oblique projection serves as an invaluable tool across various applications. Let's explore where this technique truly shines. In quick prototyping, it's like having a rapid visualization superpower. Designers can quickly sketch out ideas while maintaining true proportions on the front face. This is particularly useful in the early stages of product development, where speed and clarity are essential. For visualization purposes, oblique projection excels in helping people understand how products will look and function. Imagine showing a client a new piece of furniture. They can clearly see the front design while still understanding its depth and overall form. In educational settings, this technique becomes a powerful teaching aid. Think of explaining the shape of a complex molecule to chemistry students, or helping architecture students understand building layouts. The beauty of oblique projection lies in its balance between accuracy and simplicity, making it an excellent choice for these various applications. Let's have an honest discussion about where oblique projection excels and where it might fall short. Starting with the advantages, one of its greatest strengths is its simplicity in both construction and interpretation. Imagine reading a book in your native language versus one in a foreign language. Oblique projection is like that native language, easier to understand and work with. The fact that it shows one face in true shape and size is particularly valuable when dealing with objects where front features are crucial. Think of circuit boards or control panels. It's especially suited for objects with prominent planar features, like buildings or furniture. However, we must also acknowledge its limitations. The distortion in depth dimensions can be problematic. Imagine looking at a long corridor in an oblique drawing. It might not give the same sense of depth as a perspective drawing would. Compared to isometric or perspective projections, it might appear less realistic, similar to how early video games represented 3D spaces. And when we're dealing with complex objects full of intricate details, oblique projection might not be the best choice. It's like trying to describe a complex symphony with just a few musical notes. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.